I'm going to talk about what our resiliency efforts are, both what we did immediately after the storm, but also what we're thinking about in the long term. At about 72 hours before the storm, we started to get detailed weather reports that we would disseminate to key staff so that we could plan for closures of our facilities as necessary. We really thought that our major impacts were going to be at LaGuardia Airport, the PATH system, and the Holland Tunnel. So the storm itself had as big of an impact because of the nature of its storm surge. The time that Sandy hit corresponded to high tide. It was also a full moon, and it was a spring tide. Because of the wind direction, and the northern part of the storm pushed the water into that New York harbor. What we were being told was about 11.5-foot storm surge. It came in at about 14 feet. We actually were very lucky that there were not hurricane force winds, and we did not find any serious structural or major structural deficiencies, but we had significant electrical and architectural deficiencies. We were very prepared to inspect with structural inspectors on call for this kind of emergency. We did not have as deep a bench of architectural and electrical engineers available right after the storm. We were able to find people, but that was some sort of lessons learned that we'll have a much broader discipline base of inspectors in the future. The storm surge actually came up and over the New Jersey Turnpike and onto the airfield at Newark Airport. This is something that we have never seen before, which was, obviously damaging also on the way back out when the surge leaves. Erosion happens at that time as well. At Greenville Yards, we had a runaway barge which caused structural deficiency of this lift bridge, which has since been demolished. At Port Newark, on the right, a barge actually lifted up on top of one of the berths. Many of the buildings and the electrical infrastructure at the ports was flooded. So, there's a concern about the effect of salt water on electrical systems, and we're in the process of studying that now. Our PATH system had the most extensive flooding of any of our facilities. On the left here, you can see water coming down the stairway at the Hoboken station in New Jersey. The picture on the right is a control panel, and you can see what the salt water does to that. It's full of rust. There is, ongoing corrosion because salt, you can't just wash it away with regular water. So we're looking at what are the cumulative effects of that and what can be replaced, what needs to be desalinized. So it was a number of months that we were at partial service. Of the Holland Tunnel, which was flooded both through the portals and the vent building from surge. On the left there, you can see water is coming down from the ceiling. That's from a vent building, and the doorway down from that vent building. We had several weeks of just getting through the emergency part of Sandy, getting back up and running, making sure that everything was functional, and then we in the engineering department took a hard look at what we would need to do cross-agency to increase our flood protection, our generation capacity, et cetera. We went through a cost exercise. We went through a implementation exercise. We also established an internal mitigation team. So this slide shows solutions that we leave in place at a facility, and this is all flood protection, water intrusion protection measures. On the left, these are called concrete bin blocks. The one on the far right there are called HESCO barriers. These are sand-filled geotextile bins. They last about 5 years, so they're more of a temporary measure, and they are stackable, so we can use these where we need heights above 4 feet. This next set of measures are things that need to be put in place right prior to the storm. They're site-specific and they're use-specific. The stop logs, which would go in front of a door or a vent building, you would stack those aluminum pieces in maybe a day or two prior to the storm, as long as you don't need access to that doorway. The water-filled barriers, these we're using across roadways. These are for places where we can't shut down more than maybe a few hours or a half a day ahead of an event. The engineering department is taking a hard look at our agency design guidelines. Now we have decided to take a little bit more of an asset-specific approach and really dig into what is the life expectancy of this asset? What's its useful life? Is it 20 years? Is it 100 years? And look at the risk of that flood happening over the span of that life and show that probability. How critical is this asset, both from an emergency ops standpoint, from a business continuity standpoint, and from a regional standpoint? We're going to add anywhere from 18 inches to 55 inches of height to either a flood protection or to a first floor elevation, depending on the useful life of that asset and its criticality. So it becomes a little bit more of a complex risk-based approach. So New York City has the Building Resiliency Task Force, which is taking a look at all of the building codes and seeing where are there resiliency measures that can be incorporated into those codes. It won't be a separate resiliency design guideline book. It'll be part of how we do business.